Yeah, hello everyone again. So now we are in week 4. We continue future question, intelligent machining in the future. Okay, let's see. It's
Welcome to Module 4,
the
the future
introduction
of intelligent
courses.
machining. At the end of this
Course.
module, you will be able to explain why intelligent machining is an integral part of manufacturing process improvement. Describe the roles of IIoT or Industrial Internet of Things,
Oh,
intelligent machining,
sorry.
and big data in a digital manufacturing enterprise.
This one.
And
Okay.
discuss how intelligent machining is going to change the future of digital manufacturing. This lesson will showcase how digital manufacturing is revolutionizing the intelligent machining paradigm. Several examples of intelligent machining in distributed setting will be presented to indicate future possibilities. Vision technology combines high-definition cameras with software to identify complex geometric objects in variable lighting conditions. The advances in vision technology assist in creating intelligent manufacturing solutions, for example, robotic bin picking. Here we see two different geometric objects being recognized and picked by a robotic end effector and placed on a conveyor. This system identifies defective parts that are non-compliant and only allows conforming parts to move on to the next stage of the manufacturing process. The overall integration reduces the operator involvement and allows for a safer operating conditions. Some other future possibilities include connected machines in manufacturing software, connected factories, and digitally enabled supply chains. At machine level, the data collected during condition monitoring of a machine can be shared with other industry partners to help them identify potential mechanical issues leading to machine failure. In the future, remote operation of machines will also become feasible and easy to handle with less human intervention. Intelligent
Human
machining will
intervention.
enable the production to become more flexible and thus shrink the time to market for next generation products. Using intelligent machining, industrial Internet of Things, and big data, small-scale enterprises will adapt quickly to newer technologies and become more competitive. Intelligent machining, when combined with the power of industrial Internet of Things or IIoTs, can result in
IoT.
connected machines within a factory, which can further be expanded to connect different factories and a truly digitally enabled supply chain. This connected enterprise can be a huge enabler for the realization of the digital thread, which is generating, sharing, and utilizing data and information at all stages of the product lifecycle, from ideation to disposal, throughout the supply chain, thereby enabling stakeholders to make smarter decisions in real time.
Monetization in real time. Okay. What industrial Internet of Things machining cell. Okay, this one. Some state the need of software architecture is then a need for the computer architecture to be open. After viewing the following view, it led the need for intelligent machine. It led the year of connected free that lead to future possibility of intelligent machine. Okay. Software architecture. Reading again. On how digital manufacturing is revolution in the paradigm. Software architecture. Software architecture to mana na the machine is need for computer architecture to be open. It and the need for computer architecture to be open. Computer architecture to be open to share. Okay. Need for intelligent machine. Need.
I'd like to introduce new technology. We're
We're
actually locating the parts, communicates back with the second part of our demonstration, includes the gauging process will go to an accuracy of plus this component. So we are able to CNC screens for both alarms, I/O, teach pendant. The robot teach pendant. See the information displayed.
Okay. Open a bit to need and the object. Okay. Zero connected under free. Free connected need apply. Can be further expand to connect different factories to enable truly enable digital supply chain to enable digital supply chain. Further future was intelligent machine here again. Smart manufacturing to possible smart factory and intelligent machine smart factory and connected factory. Okay. Okay, so we read again. We not correct, but we see the answer here. Software architecture to materialize idea to order. Software system to materialize an idea to others. It needs learning and designing. Architecture is a design and method of constructing any physical structure just like that. The software that we use in our day-to-day activity also need to have an architecture to help transform the idea for the software to usable software so that a software architecture is requirement to materialize an idea to a product, an idea to a product. Computer very generally code are frozen locked by the software run the task prevent ability to user to maintain customization while the software intelligent However, sometimes users recognize the need to modify the source code after purchasing and integrating the software again. Yeah, want to customize to the high level of customization. Open software architecture allows users to modify source code to gain it higher level of customization. As you can see from the following video, intelligent machining is together with two process into single entity. Here we can see the robotic arm help in picking the right component using machine vision and insert into the chuck for machining operation. What this is reduce the operator involvement and allows for several operation conditions. See together two different process into single entity. Let's say robot arm have to pick the right component using machine vision, insert into the chuck, chuck for machine operation. Well, yes. Connect after free can be huge enabler for realization of the digital field, generating, sharing, and utilizing data and information for all step of product or system life cycle from idea to disposal to hold the supply chain, thereby enable stakeholders to make smarter decisions in real time, Okay. Future possible intelligent machine load using intelligent machining, industrial Internet of Things and big data enable small scale enterprise to adapt to newer technology. Okay. The production become flexible and time to market become less than the production become flexible. Data collected during condition monitoring of the machine. Data collected during condition monitoring of machine can be shared with other industrial partners to help them identify mechanical issue before happen in the first place. Remote operating, remote operating of the machine become feasible, and easy to handle with less human intervention. Data collecting can be shared to help identify remote operation. Okay. Adapt new technology. The rotation become flexible and time to market become less. Okay. TED Talk on methodology.
Welcome to DMD Tech Talk. As your moderator, I will take you into companies where we will have conversations with industry partners who share our manufacturing passion. More specifically, they share our passion for how digital manufacturing and design is transforming the industry. We are extremely fortunate to be able to share some firsthand experiences with you. Today's focus is on metrology, defined by the National Institute of Standards and Technology, or NIST, as the science of measurement. We will visit Buffalo Manufacturing Works in Western New York. Buffalo Manufacturing Works helps innovation-driven organizations excel by partnering with their internal manufacturing, engineering, and research and development teams to grow, compete, and deliver better products. Let's go inside and hear from our industry partner about advanced technologies in metrology.
Additive manufacturing is an exciting new paradigm, but also gives us new, exciting, and challenging inspection requirements. So traditionally on machining and finishing, we know what to expect. We know that if we pass a mill across a surface, that the surface roughness should be consistent in that area. And our standards have been built around these assumptions. Now, in the world of AM, we cannot make those, and that forces us to be much more dynamic and diverse in how we inspect our parts. So before, when we could take a single one-dimensional scan or a linear scan across the part, we're required to look broader, take full three-dimensional images of our part to understand where the process parameters inspect for the full part and how different features on the surface may affect the process as it goes. The field of metrology has been for a long time stuck in tactile methods, both tactile roughness gauges, which scan a sharp tip across the surface, as well as CMMs, so large coordinate measurement machines, which scan balls over a surface. These are still often used, but they come with all of these assumptions built in. So we're seeing optical techniques come in a much wider sense now that the application space of AM and new fast machining techniques require it. The exciting part to come is going to be closing the manufacturing loop. So taking the data we see with our optical inspection techniques that enable us to measure quantities much farther than SPC, so looking at 100% of parts, analyzing the data and using that to close the feedback loop to educate the process and increase the efficiency of your manufacturing cycle. That loop closing I see as the next big move in metrology. In our lab at Buffalo Manufacturing Works, we have a range of different pieces of equipment. On my left, this is a Brooker low coherence optical interferometer. This system images a surface in 3D. So when it's operating, you see a cloud of light, just like you would out of a microscope, and you're imaging that full cloud of light simultaneously. So you're taking a 2D image. And then it uses a scan mirror and the wave nature of light to reconstruct a 3D image. This can be done incredibly accurately, down to 1 nanometer resolution. The power of this technique is not just the resolution, but your ability to take full 3D information on a part. We have a multi-center integrated package with custom integrated motion control. So this system is designed to answer a customer's need for flexibility, running on a 50-part family. It allows the customer to get both form measurements, so the dimensions and the GD&T measurements, down to 10 micro-inch accuracy, and it also allows roughness measurement of a part. And finally, it allows all of that data that you take to be simplified and tell you if the part is good or bad with a relatively fast cycle time in the minutes range. The optical techniques require optical access, so if you can't see it, you can't measure it. Combining motion, be it robotic, be it precision stages, or be it conveyor belts into the process allows you to both use what you have already in your process, using the robots, the conveyors you have, to take measurement instead of requiring you to take your parts offline to measure them on the CMM, and also allow you to get the optical access you need to take the data. So it's very much a win-win for both the inspection of equipment and getting to something like 100% inline inspection.
Okay. Evaluation. Okay, we almost finished. Closing. Okay. One advantage of IoT means stand upon training, maintenance upon training, part measurement offline, rest during downtime, remote diagnostic, machine sensor can resulting check KO machine adjustment can result machine adjustment quality part disruption to downstream process disruption to downstream process machine adjustment quality part disruption to downstream processes disruption with intelligent machining. You are able to connect machine between a company via wireless interconnectivity. You are able to endorse maintenance plan when you first implement your intelligent machine into your factory. You are able to include maintenance plan. Yes. Product cycle will be shorter. Product cycle shorter. Review product cycle will be the same. Product cycle. Yeah. Some application of battery machine use manufacturing, utility, retail, healthcare, Yes. Or digitally connected machine can also be extended to digital connected factory to maximize productivity and minimize costs. Closed loop system. Closed loop. Artificial intelligence, machine learning, control system, robotics, and smart sensors are intelligent machining tools. With the following are important of incorporating intelligent machining in the factory. Advanced information, reduce operation, reduce maintenance costs. RFID chip talk to machine. Demonstrate how the future vision for manufacturing will data. Okay, let's see. Interval production.
A vision of tomorrow's manufacturing. Products finding their way independently through the production process. In intelligent factories, machines and products communicate with each other, cooperatively driving production. Raw materials and machines are interconnected within an Internet of Things. The objective, highly flexible, individualized, and resource-friendly mass production. That is the vision for the fourth industrial revolution. A look back at history. At the end of the 18th century, the first steam engines and the intelligent use of hydropower revolutionized production. The late 19th century saw the rise of electrical engineering and mass production. The first moving belt conveyor was used as long ago as 1870 in the slaughterhouses of Cincinnati, Ohio. In the mid-1970s, electronics and IT began to expand rapidly into industry. Siemens developed the first SIMATIC. Production became increasingly based on computer-assisted controls. The fourth industrial revolution is still a vision. Experts believe that it will only become a reality within the next 20 years. In intelligent factories, everything is interconnected wirelessly. At the German Research Center for Artificial Intelligence in Kaiserslautern, this future can already be experienced right now. Research is underway here into exactly what the industrial production of tomorrow will be like.
Fabriken werden zukünftig aus Bausteinen bestehen, aus smarten oder intelligenten Bausteinen, wie man es nennen mag. Vergleichen wir das vielleicht mal so ein bisschen mit einer Lego-Steinwelt. Das heißt, wir haben standardisierte Bausteine, die wir hoffentlich relativ einfach zusammenstecken und zusammensetzen können. Jeder dieser Bausteine hat bestimmte Funktionalitäten und wir können sie zukünftig in einem solchen fabrikinternen Internet dann kombinieren.
A bottling plant for liquids, set up together with Siemens, is used to demonstrate the most important components of the intelligent factory of the future. Each bottle contains an RFID chip storing a precise description of how it has to be processed, which liquid, which lid, and which label. At each station, the bottle communicates directly with the machine, telling it how it has to be processed. At the end, a computer checks whether the bottle has actually been produced as desired.
Smart.
Factories with networked machines and products are already in existence today. In the future, however, these hitherto self-contained systems will be connected together in a comprehensive network. All devices, machines, and materials will be duly equipped with sensors and communications technology and connect to each other. These systems are known as cyber-physical systems. The highlight is that they communicate with each other and also control each other cooperatively.
Wenn Sie sich das Thema Industrie 4.0 angucken, dann basiert sie ja auf der Logik dieser Cyber-Physical Systems. Das heißt, Sie haben autokrate selbst arbeitende Systeme, die sich optimieren und sich gegenseitig austauschen und dadurch letzten Endes Produktion optimieren.
Ja, die Vision sieht so aus, dass wir ein Internet quasi hinunterziehen bis auf die unterste Ebene. Das heißt, jeder Sensor, jeder Aktor wäre damit quasi ein Teilnehmer eines Internet der Dinge. Jedes Gerät hat damit eine eigene IP-Adresse, ist damit adressierbar in diesem Netzwerk.
For the customers, this means tailor-made products at relatively affordable prices. For industry, it means highly flexible mass production that can be rapidly adapted to market changes. Because in the future, product life cycles will be even shorter. Another reason why it's increasingly important to depict engineering across the entire life cycle. Maintenance, for instance, is planned in from the very start.
Wir haben ja bereits in den 90er Jahren mit Totally Integrated Automation entsprechend ein Setup gewählt, wo unsere Produkte und Systeme sehr gut miteinander kommunizieren können.
At corporate technology in Princeton, a cyber-physical control is being researched even today. The vision, the control, and all linked sensors are connected to the internet.
One potential scenario is enabling the PLC to react to utility pricing information in building automation. We can enhance PLCs to use simulation to calculate how much to pre-cool a building, with the ultimate goal of turning off the cooling system during peak times.
But that's just the beginning.
With prototyped capabilities in a PLC, to access big data in cyberspace in real
9
time.
years ago.
And we've also enabled a network of PLCs to connect to a dynamic
Very
simulation of the
old.
entire physical
Who's this
process.
pattern?
Siemens is shaping the future of industry. Connecting the real with the virtual world of production is making it possible to enter entirely new dimensions in quality, efficiency, and flexibility. The company is well prepared for Industry 4.0.
Okay, it's 9 years ago already. Very old courses. Okay. Let's go. Maybe should be the same. The same. The red light cycle. Two. Quantity. Machine treatment. More diagnostic. Ah. Longer red light cycle be longer using. What the hell? Really? Product life cycle. Radio. Okay. Glow. True. Okay. Product life cycle be lengthened using correct enough using machine. Should be shorter. Maybe this one is wrong. Yes. Back. Back. What the hell? This one. This one correct. In Latin American. What the hell? Yes, we cannot take it again anymore. Specialization project. Okay. Key takeaway. So yes, we do it later. We do it later. Okay, see you next time.